All right, this video is one of our last videos about what I like to call the three-letter theorems, and this is all going to be about angle, angle, side. In class, you should have done this exercise, so we're going to jump down to the bottom of the first page here and talk about what angle, angle, side actually is. So angle, angle, side is given the fact that you have two triangles, ABC, and then ACB right here. If I have two angles, so let's say B and B prime, and then C and C prime, if I have two angles, and then I'm also given the non-included side, two angles, one side, then the triangles are congruent. So basically what this says is, instead of ASA, where you have two angles in the included side, we're now saying AAS also works, two angles in the non-included side. So notice the side is not between the angles. Okay? So all that means is now when we do a triangle proof, if we end up with this figure where we have two angles on the non-included side, that's good enough to say that the triangles are congruent. Now, why does that one work? So what we can say is if one pair of So why does AAS work? If we look at the diagrams down here, if we take a look at these guys, it's been given just by the markings in the diagram that if we know that angle B is congruent to angle E and angle C is congruent to angle F, we can then also say that A would be congruent to D. And let's think about why. Well, let's say if angle B is congruent to angle E, and let's say magically that I knew that these were both 100. And I knew that C was, let's say, 30, making F 30. I now have 130 degrees here. This has to be 50. I have 130 degrees here. That has to be 50. Since two angles of a triangle really force the hand of the third angle to have a certain degree, as soon as you know two angles of one triangle are congruent to two angles of the other, those third angles have to be congruent. So if B equals E and C equals F, then A has to equal D, meaning that we could have also said ABC is congruent to DEF by angle side angle, which really means AAS is good enough. I don't need that third angle to do that, and AAS will also work. All right? So, in proof, we can now use the following new reason, and that new reason being angle, angle, side congruence. And we can also use another new reason if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. Okay? Now, we have now talked about AAS. We've talked about SSS. We've talked about SAS. And we've talked about ASA. So if I take a whole bunch of combinations of A's and S's, I can get these. The ones that we haven't talked about are SSA or ASS, and we haven't talked about AAA. Well, the reason we haven't talked about them is they don't work. SSA will never work because of this diagram right here. Here's a 23-degree angle, a side of length 11 and a side of length 9. Here's a 23-degree angle, a side of length 11 and a side of length 9. Are these triangles congruent? Absolutely not. The reason that they're not congruent is because if I think about this 9 right here, it can swing kind of like a vine over to here and still have a length of 9. making triangle number 1 and triangle number 2 not congruent. You can see it down here because we've done it. The 9 can be outside and the 9 can be inside. So if you have one angle and two sides, but the angle is not between the sides, you cannot prove the triangle is congruent. It does not guarantee congruence, and it's because of this. So basically SSA, and sure, I'll write it ASS, these are not okay. Reason being this diagram right here. Moving a little bit forward, what about AAA? So let's sketch a small equilateral triangle. There's an equilateral. If this is equilateral, all the sides are the same, and therefore so are the angles. And in an equilateral, I got 60, 60, and 60. Well, what about this guy? Isn't this equilateral also? Absolutely. These are still 60. But are these two triangles congruent? No, they're not congruent at all. I can make things bigger, keep the angles, but change the sides. So no, AAA does not guarantee that two triangles are congruent. All right, so AAA, not okay. SSA, not okay. ASS, not okay. So now we're just going to do two proofs, and then we'll be done practicing with AAS, and you will practice some more tomorrow. So remember, as we go through these proofs, the reason that we're flipping these lessons is we want you to focus on getting the proof right the first time and having basically something to fall back on when you're working alone. You can say, well, this reminds me of that other proof I did in the notes. Let me look at that one, and that one's going to help you with the next one. All right, so we are given that AB is perpendicular to BD. Okay, so that's going to be right. And CD is perpendicular to DE. And AE bisects BD at C. So C bisects something. Prove that the triangles are congruent. Okay, I can do that. So we have statements. We have reasons. And my first clump of statements comes from the givens. So take a second while I'm doing so and rewrite your givens. AE bisects BD at C. Given. Okay, whew. So I've rewritten the givens. All right, the next thing I probably want to do with this, let's deal with the perpendicularity. You need to know that when you have perpendicularity, two steps emerge. Step 1, identify the right angles. Angle ABD and angle CDE are right angles. Why? Because perpendicular lines form right angles. Then, because they're right angles, they also have to be congruent. Because if they're both right angles, they're all congruent. All right angles are congruent. You need to remember that when you see perpendicular, it forces your hand into writing two steps about that perpendicularity. Identify the right angles, state that they're congruent. All right, so I have that taken care of. The next thing that was up in the given was this word bisect, so I should probably use that. BD got bisected at C, so this guy got bisected, making these two halves equal. That makes sense, right? So BC is congruent to CD because bisectors cut a segment into two congruent parts. All right, so I have those two things, and then let's see, I also have this guy right here and that guy right there. So number 5 is going to state that angle BCA is congruent to DCE because they are bow ties. It's a vertical angle. And vertical angles are always congruent. And then I'm going to look at this and I'm going to say, all right, what does that mean? Do I have enough for the triangles? I do have enough for the triangles. I have 3 parts. I have an angle, and another side. But since the side is in the middle, is this AAS or ASA? Well, this would in fact be ASA So triangle ABC is congruent to EDC by ASA. Now, I know we just talked about AAS, but I put this in here to remind you, AAS and ASA both work. You have to make sure you use the correct one when you're talking about these. All right, and moving down here, last but not least, I have another proof. I have statements. I have reasons. I have my givens. And this is given. Okay, so you should be writing your givens. Then let's mark the diagram. DC, BA, ADC, this guy, and CBA, that guy, and AD is parallel to CB. All right, so I have that. Now, step 2. Forewarning, I'm going to write step 2. It's actually not going to help us, but I'm going to write it anyway because that's okay. One of the things I always tell my students is you should look for things that you automatically know to be true, like reflexive and vertical angles. And when I look at this diagram, I see this reflexive. It jumps right off the page. So whoops, what just happened there? I don't know. So AC is congruent to AC by the reflexive property, right? That is 100% true. I write it in the diagram. I go, hey, look, I have an angle and two sides. Uh-oh. This is ASS. That's not enough to prove the triangle is congruent. So I can't do any three-letter theorem. It's not wrong that they're reflexive. You can write it down. It just doesn't really help you much. So I need to look for something else that's helpful. Oh, wait a minute. I haven't used these arrowy things. Those arrowy things mean parallel, right? When you see parallel lines in a proof, you are usually looking for corresponding or alternate interior angles. In this case, we are going to see some alternate interiors. It's going to be this guy is alternate interior with that guy. But Mrs. Weber, why isn't it that the little angle up here is congruent to the little angle down there? Well, because we don't know that DC and AB are parallel, right? When you are given parallel lines, your alternate interiors need to touch those parallel lines. And if they don't, you don't know that they're congruent. So it has to be this angle right here and that angle right there, angle DAC and angle BCA. Because if lines are parallel, then the alternate interior angles are congruent. Then when I look at my diagram, I have two angles and two sides, but with those angles and those sides, this is not the included side. So this is AAS or AAS over here. Doesn't matter which one you think about. Triangle ADC is congruent to triangle CBA, reason being AAS. So there is our notes for the day. We have everything. We have AAS and ASA, and you should hopefully know the difference between them. You should also know that ASS, SSA, and AAA are a no-go. You can't use them ever, so don't write them down. All right, we got to end with a joke. So the joke today is going to be a pirate joke. What did the pirate say on his 80th birthday? And he said, "Aye, matey." Bye.